All right, welcome to today's video, which is on special right triangles and trig applications. We are going to be talking about two different special right triangles today, a 45-45-90 triangle and a 30-60-90 triangle. So let's just start with 45-45-90. Now, we know by theorems in geometry that if we have a triangle that has a 45-degree angle, that means that this angle down here also must be a 45-degree angle as long as this is 90, because the interior angles of a triangle have to add up to 180. So I'd have 90 and then 45 and 45 make 90, giving me 180, which tells me that these two sides are also equal, meaning that one would also be x. So if I name my two sides that are equal, which by the way is an isosceles triangle, I can use that to find my missing side length. So let's see if we can write out that missing side length, the hypotenuse in this case, in terms of x. I've got 45 here, 45 here, so I know that that's x and x. Using the Pythagorean theorem, since it is a right triangle, I know that x squared plus x squared is going to be my hypotenuse squared. Well, x squared and x squared is 2x squared. And then I need to take the square root to get c by itself. Now, the square root of x squared, this is a perfect square that's going to come outside. So I'm going to have x, but the 2 is left underneath. So x root 2 is equal to c. Now we can use that to find missing side length in a 45-45-90 triangle. And we can do this to avoid using the Pythagorean theorem or some SOHCAHTOA. This is kind of a little shortcut to using SOHCAHTOA. Let's take a look at example 1. So in example 1, you have a 45-45-90 triangle. You know that this angle is also going to be 45, and that means that this side is also going to be 4, which means that this side has to be x root 2. So if 4 is equal to x in my triangle, because that's my two sides, that means x equals 4. So x root 2 is going to be 4 root 2. That's my missing side length. Okay. In number 2, this one's a little bit trickier. For number 2, now I have the hypotenuse. So I have the side that's equal to x root 2. Well, if 5 root 2 is equal to x root 2, then 5 must equal x. So 5 is equal to x. Okay, and that gives me the missing side, or two sides in this case, since they are isosceles. So let's now look at number 3 and see if we can figure out that one. Number 3, a little bit tougher. Now you know the hypotenuse, so you know that this is equal to x root 2. This is where things get a little interesting. You've got 12 is equal to x root 2. You need to find x. So you're going to divide by the square root of 2, divide by the square root of 2. So I've got 12 over the square root of 2, which is equal to x. Now that's all fine and well, except that we are not allowed to leave the square root of 2 in the denominator. And we talked about this a little bit in chapter 5 last trimester, or in Algebra 2A. So the way I fix that is to rationalize the denominator. I need to make that denominator a rational number, or in other words, a number that ends or terminates. So I'm going to multiply by the square root of 2. Because if I multiply the square root of 2 by the square root of 2, I end up with 2, which is a rational number. But we all know that if I do something in the bottom, I also have to do it in the top. So now I have 12 times the square root of 2 over the square root of 2 times the square root of 2, which is 2. Now there's one other thing I can do to simplify this. 12 divided by 2 is 6. So I get 6 root 2 is equal to x. Now, one thing that I want to point out, it says, do I need to use these patterns to figure out the missing side lengths? No, you do not have to. These are just shortcuts that kind of help you speed up the process. But you can always continue to use SOHCAHTOA or the Pythagorean theorem to find the missing lengths. You do not have to use the patterns. Like I said, these are just shortcuts. Let's take a look at a 30, 60, 90 triangle. In a 30, 60, 90 triangle, now we can take a look at what those side lengths will be. I took two 30, 60, 90 triangles and backed them up to each other here. So you can see that that's one and that's the other. With my 30-degree triangles matching up at the top, 90 degrees at the bottom, which means that that has to be 60 and that has to be 60. Now what I've created here is a triangle that has 3 equal side lengths, or in other words, an equilateral triangle. So with that equilateral triangle, I've also named this side length to be 2x. The reason I can call that 2x is because now this is also 2x and this is 2x. Well, if this side down here is 2x, then when I cut it in half, each one of these pieces is x. So if we go over to our one that's just pulled off separate here, I know that I've got an x there and a 2x there, and I'm missing that. So I can use the Pythagorean theorem to find the length of that side. I have a leg in the hypotenuse, so I have x squared. I'm missing the other leg, so I'm going to call that b is equal to 2x squared. Now the whole thing 2x needs to be squared, which is why I put it in parentheses there. So I've got x squared plus bx, or b squared is equal to 2x squared, which if I square both parts is 4x squared. Now I'm trying to get b, so I'm going to subtract x squared. 4x squared minus x squared is 3x squared. Okay, and then again I want b by itself, so I need to take the square root. I can pull that x squared out front again, and I have x square root 3. So that becomes my missing side length. Now I can use these patterns in numbers 4, a, and b to figure out what side is missing. So in this case, I know the hypotenuse, which is equal to 2x. Well, if I know the hypotenuse is 2x, then I have 2x equals 10. I can divide by 2 and get x equals 5, which means this has to be 5. I know that that missing leg up there has to be x root 3, so that means x root 3, since 5 is x, is going to be 5 square root 3. So I've got the two missing values. X is equal to 5, y is equal to 5 root 3. In part B, now I am missing the hypotenuse and the x term. So that means if this is the hypotenuse, that means that has to be 2x. That's x, and this is x root 3. So we're back to that problem of having 12 equal x root 3 and having to rationalize the denominator. Because what happens here is I have to divide by the square root of 3, and 12 divided by the square root of 3, I can't leave like that. So I'm going to multiply by the square root of 3 to get that radical out of the denominator. I have 12 root 3 over 3 is equal to x, and then 12 divided by 3 is 4, so 4 root 3 is equal to x. Okay, well, if that's 4 root 3, then 2x must be equal to 2 times 4 root 3. 2 times 4 root 3 is going to be 8 root 3. So there's your 2x, and there's your x. So again, they're just patterns. They just are patterns to recognize that make things go a little faster. But if you wanted to continue using SOHCAHTOA for all of these, you'll get the same answer. Let's flip over to the back and take a look at just number 5 and see how we do there. We want the exact value of the sine of 45. Now remember, when we talk about exact, that means that we are not rounding, we are simplifying a radical. Let's draw out a triangle for this. Sine of 45 means I have a 45, 45, 90 triangle. So I have two sides that are the same. There's my right angle. I'm going to call this the angle that I'm looking at. So that's my theta, or that angle that's missing, or that I'm looking at, and I know it's 45 degrees. So I want the sine, which is the opposite, this side across, which is the x over there, over the hypotenuse, which is x squared root 2, right there. So that means sine of 45 is equal to x over x root 2. X over x root 2, I can't leave it like that. So I multiply by the square root of 2, multiply by the square root of 2. X over x cancels out, and I'm left with the square root of 2. Those two combine and be 2. There's your value. In number 6, you're looking at the exact value of tangent of 45. So again, I'm going to draw that 45, 45, 90 triangle. Again, I'm going to look at that 45-degree angle down there. And this time, tangent is going to be opposite over adjacent. So tangent of 45 is equal to x over x. Well, we all know that any number over itself is equal to 1. So the tangent of 45 degrees has to be 1. We're going to go ahead and stop there for today. We'll finish up the last few examples tomorrow in class. Have a great night. I will see you tomorrow.